Hello all, in this video we will see various losses that are associated in a PCB which causes signal attenuation, and also basically it results in signal integrity issues. So, so the first one. So basically whenever we have a PCB designed, we always think that everything is ideal, but in practical there are many variations which during the design stage we might not think of, but these might come post the design stage. Let us look at some of them. So the first thing, copper traces. So when we route the copper trace on a PCB, we route the trace with a specific width to meet the impedance requirements, and also we route for a specific distance between the transmitter and the receiver, or the driver and the receiver, right? So we always have a specific copper width, right? 0.5 ohms or 1 ohms depending on the requirement. Now that means the in reality, ideally, the trace of the copper is always rectangular in shape. That is what is the ideal nature, right? But in reality, copper traces are trapezoidal in nature. This is because of the um, fabrication requirements, where you see here on the left, this is how we think the PCB will come to us. But actually, after etching, the PCB traces are actually trapezoidal in nature. That means whatever the analysis that we do with a square with rectangular copper trace is actually not valid, and it is actually, the traces are actually trapezoidal in nature. So that is one of the important variation in a PCB that we get in hand. Now the second thing, again this is one more scenario where the PCB trace, okay, as we see here, this looks very smooth, right? This is how we represent in images, or when we try to route it on a PCB, we think the PCB trace is as smooth as we see here. But actually, the PCB traces are not smooth. They are actually having a rough surface on the top, as we see here, and the signal actually has to go through this rough surface, and this basically is represented by the surface roughness. And due to that surface roughness, we have signal quality loss. That is one of the important parameter that need to be considered while the fabrication of the PCB is done, or when we have the PCB in hand, we should remember that the PCB that is fabricated is not ideal in nature. So, if we move to the next point, one more important point is the dielectric, right? The dielectric plays a very crucial role in the performance of the PCB, whether it be impedance, whether it be PCB stability, whether it be operation with respect to temperature, that means giving rigidity to the PCB. All these dielectric plays a very crucial role, and this dielectric, as we know, is sandwiched between two copper layers, right? Whether it be ground to ground, signal to power, or power to power, there can be various scenarios. Now, now in reality, or in an idealistic case, basically, we think that we select a PCB material with a specific dielectric constant, but dielectric constant over the entire PCB material is not constant because of its construction, the electrical properties. There is always a variation in the dielectric material. So that means the impedance that we think is absolutely ideal and uniform across the transmission line, and we say we have a controlled impedance, is not a true statement, right? That means there is definitely some impedance, whether it be minimal or whatever. Because of this dielectric constant variation, there is impedance variation. Okay, now considering all these factors, okay, what are all the various problems that we would see in the PCB? Ultimately, we see signal integrity issues. That's a simple statement. But what are the different issues that cause these signal integrity problems? The first thing, trace impedance variation, right? As we have mentioned that delta constant is not uniform, there is every chance that the trace impedance might have a very slight variation. But again, very slight variation means different um, uh, effect on signal at different places on the PCB, and it will definitely lead to variations in the PCB performance, electrical performance, right? And as we have talked about surface toughness, as we have talked about the nature of the copper or the size of the copper, definitely there will be trace delay that will be seen because of the various characteristics associated or the changes that we have talked. And then the dielectric losses. So again, these dielectric losses we have discussed because of the dielectric losses. So if we categorize, there are two types of losses in the PCB. One is conductor loss, and second one is the dielectric loss. So conductor losses are within the conductor. Dielectric losses are due to the dielectrics that are present in the PCB, right? So these dielectric losses would contribute to the attenuation of the signal, thereby signal losing its integrity. And ultimately, all these lead to losses in the transmission path of the signal, or losses in the PCB trace that is laid out, and we all see different signal integrity issues, whether it be signal losing its actual form and or we should say actual size or actual shape, and then signal extending into time of the next data, and ultimately interfering with the next bit, thereby causing intersymbol interference in the channel. So and then the signal losing its strength over a period of time. All these various issues that we see are due to the various factors that we have talked here. Please post if you have any questions on this. Please let us know your opinion on this video. Thank you.